Hello guys, Cyprien here from FEA for All, and in today's video we'll have a look at a very interesting simulation. So it's a spring that we will analyze with three types of nonlinearity. So it's a very complex analysis. There will be nonlinear material, there will be large deformation, and there will be nonlinear contact. So I have avoided to make this kind of simulation until now with Salome Meca because it's very complex. You have a lot of things to think about. You need to very good mesh, you need to do a lot of tests, and you need to understand how everything works, especially nonlinear, elastoplastic, hardening curves, nonlinear contacts, different kind of convergence methods. All of that is extremely hard. So I decided to split this video in two parts, and you will see I have done some mistakes during the process, but I decided not to edit it because it's much more valuable for you to understand from my mistake, to see what kind of error I get and how I solve this kind of error. And this is basically what engineering is about, right? You have to understand how to go over the problems in order to make your simulation converge and get your results. So that's what we'll do in this video, and I hope you will like it, you will find it useful, and you will learn a lot from it. So if you do, please leave a comment, please like this video, please subscribe to my channel. That's a big boost for me, and it helps really a lot. So thank you very much, and let's go for the video. Okay, so let's start by opening Salome Meca. I'm on Ubuntu 20.04, and I will start a new session. So let's create a new folder, and let's start in the geometry module, in which I will import my CAD model. So let's open Geom, let's import my CAD model in step format, leaf spring. So now you have a message telling you that you have to be careful about the unit. So do you want to take the account in account the unit embedded in the file? So I'll put yes. So you don't see anything, so click on here to make it bigger. So here it is. Now what is very important first is to understand the units of this model. So because it looks big on the screen, but we don't know if the unit that have been used is millimeter or meter, and following that, the material properties you will have to assign, the units of all the physical stuff that you will get afterwards will depend on the actual unit of this model. So let's check that. Let's go in the inspection. Let's use minimum distance tool. So with this tool, what you can do is you can select some elements of your model, and it will give you some dimension. So the length of this model is 0.081. So it means that the unit is meter, because if I and the whole spring is 8 centimeters long, right? So I am in meter unit, so it's good to know, and I will use this information to set up the right material properties afterwards when I will be running the code Aster study. Now let's talk a bit about how to make this simulation easier, because I'm always repeating something very important in FEA simulation, and also it's actually valid everywhere in your life. If you want to do something complicated, start with something simple. So break down the problem in something which you're almost sure that you will be able to solve it. So if I start by saying, okay, I want to do a nonlinear analysis with elastoplastic material, contacts, and large deformation, everyone which is in the simulation realm will tell you, well, you're crazy, doing that in code Aster, it's extremely difficult. So the way to start is to say, okay, I will start with something very simple. So only the spring, so I will remove the contacts, and I will remove also the large deformation nonlinear and the elastoplastic material, and I will only run that as an elastic material, which is basically just a spring fixed one part. So this is the first step of the simulation, and this should be very simple to do if you know how to use code Aster. So so you see that when I import the small, it appears like that, like one entity in my geom tree. So the first thing I have to do is to split that into the two solid bodies. So there is a command called explode, which will explode into solids. So if I do that, I now have my solid here. Oh, and the plate actually disappeared. That's because I split and I kept only the solid. So if I want to get the plate end spring, I'll just reuse this command second time and split with shell or face, maybe face. Let's try face. Okay. Okay, so now it split all the faces of this. So yeah, so let's just keep only this. So it's the face 11. So I'll just delete all those. Okay. Okay, and now I have the small split into the solid and the face. Now I will start with only the spring, so I will hide this plate and start with only the small here. And what I need is to create some geometry groups. So what I'll do is I'll apply a displacement or force on the top of this, and I will fix those. So I need to have some geometry groups. So let's create surface groups. Okay, so it's I know why it's showing up this. I select this, show only selected. Okay. Yeah. So okay, I know it's because I selected this face when as the main shape. Okay, let's redo that. Let's hide this. Let's select the solid. Make sure you select the solid. Right click, create group. Okay. Create on the face. Now I can click here and then shift key, click on the other face, click add. So you have the two faces here. I'll call that contact spring. Even if for now there will be no contact, it will just be fixed. I'll still call it contact. Apply, then select the top surface, add, and let's call that load face, for example. Apply, and I will need also to have the full volume of this. So maybe not for this simple analysis, but I know I will need it later on for the contact or something. So let's create a volume, and this will be spring volume. Okay. Okay, so now I have those three geometry groups. Let's save the study. Let's go to the mesh module. So initially I'll just mesh it in tetra because my first simulation is just a simple elastic simulation, so this will be perfectly fine. But you'll see that when I will go into nonlinear, I'll have to be much careful about the mesh. And for the contacts here, I'll need to use very good mesh. So I'll show you how to modify the geometry later on in this video. So let's start with that. Let's create a new mesh here. So this is a 3D mesh using this NetGen algorithm. I need to put some hypothesis. So this size is like the whole size of this, so it's max size. The min size is what will really determine the size of the mesh. So maybe let's choose that to start with, and let's see if what I'm getting. Okay, so I have 1,300 nodes and around 1,500 tetra elements. So there's only one layer of element, but you know, this is just a test study. It's not supposed to give me accurate results, so I don't really care about the mesh size or anything. This should work, right? Okay, so I got this mesh. Now, next step is to create the geometry groups from those groups here. So mesh, create groups from geometry, select those three groups. You see they appear here, apply and close. And now let's check that this is okay. So I got those contact spring. I got this load face as well. I got, so I don't know why I got it twice. Maybe I clicked twice on this. So I'll just remove those. And spring volume is the whole volume mesh. So that's fine. Save again. Now let's go into Aster study and let's launch linear static simulation of the spring. So let's choose the stable version of the code Aster solver. So starting from nothing, and what I'll do is that I will use the assistant because it will be much faster to create an isotropic linear elasticity study. And that will give me the comments I need to use for that almost immediately. So I have the mesh, this is 3D, Young's modulus, so that's here. You need to be sure about this value here. So if I am in meter, I need to enter that in PA. So it should be 2.1 power 11. So let's count the number of zeros. 1, 2, 3, 6, 9. So it's fine. It's the right unit. It's automatically selected meter. It's fine. Now boundary condition. So I will fix the contact springs, and they will be fixed. So 0, 0, 0. Next, pressure on mesh group. So yeah, this assistant only assign pressure, so you know, I'll change that a bit later, but for this study anyway, it should be fine. So let's put, I don't know, 100 PA is maybe, I don't care about the value, 100 PA, we'll start with that. And now we have to set up where my results will be. So I'll put that here. So let's use like that. Let's select and the unit will be RMed. And now you see I got everything to, and actually if I run that, so I don't have the model, so that's because I have to double click on this comment here. So let's just check all the comments that have been created. The first one, read mesh, is, so in French, lire maillage means read mesh. Second is affect the model, so it creates a 3D modelization of for the mechanical problem. Then you define the material, the units are correct. So I assign the material to the whole model, I assign the boundary condition, I assign the load on the face here, which is fine for now, and the simulation will be static. Okay. So I don't need to calculate stress for now. I don't care about this. I'll add that later. So this should be fine to start with and see if this works. So go into history view, current case, add that, click on run, change the auto refresh to 5 seconds. And let's wait a bit and hope that it runs. Should be. Okay, so it's green. Let's just check how long it took to solve that. So it was pretty quick. So where is it written? So just at the end. So 0.07 seconds. So yeah, well, very fast. So, okay, now let's have a look at the results. So there is the post processor, so you can right click and post process. It will automatically create, I don't know, some kind of link with Parvis and open that. And here I have a simple version of this. So this is what the linear static with fixing of the boundary condition gives me. So, okay, the color is a bit weird. So maybe because, I don't know, my so, okay, displacement and the way the color is not showing up. Color bar continuous. Let's have a look inside Parvis. I don't know, maybe that's a bug of the post processor. So let's open that into so that's this one. Apply, and yeah, now I got the color. So I don't know why in the custom post process I do not get the colors. Maybe that's a bug. Oh, anyway, it works here. So displacement magnitude is very small, so it's just because my load that I applied is very small. But the purpose of this simulation is not really to get exact result, is to actually see if my simulation works. So if you want to see the deformation, you have to go and add a filter, common warp by vector, and so I don't see anything, so I have probably to increase a lot the scale, and you see I get something like that, which is really not very realistic, and for several reasons. One, the mesh is not good, it's fixed here, I apply the pressure on it, so it's probably accumulated at the center or something like that. But at least it's working. So the first step of my simulation is okay. Now second step is to change the force into the pressure into a displacement. So let's delete that so it doesn't take any too much memory. Come back to Aster study. Let's modify this load, and instead of having pressure here, I want to apply a displacement. So I think I have to create a DDL impo, and select my load face. Then the displacement will be in Z direction. So it will be 3, let's say minus, let's try minus 1 millimeter, because we are in elastic, so we can't put too much. Oh yeah, and I'm in meter unit, so don't forget about this, 0.001 if this is 1 millimeter. Otherwise you'll apply 1 meter of deformation, right? And also let's constrain the two other direction and put that as 0. Let's save and let's run again just to check the difference. Okay, so let's open Parvis again. Okay, and now it looks already much better. You see that the displacement here is applied on the whole surface on the top. And let's apply again the warp by vector filter just to see the deformation. let's increase that, and we see that the deformation is already much more realistic. So, but of course it's just a test study, so this, for the moment, this is just the first version of force simulation. So now let's talk about how to make this simulation a nonlinear study by applying elastoplastic material curve and how to enter the hardening curve into code Aster. In order to turn this model into a nonlinear simulation with elastoplastic hardening curve, I will need to make a few changes in this model. So I have another video about the plate with a hole in which I'm showing in very much detail and talking about this nonlinear static way to analyze things. So if you really want to go into more detail about this process that I am gonna do here, I recommend you to go and watch that video. Now I will still try to be as much precise as I can to make it easy to understand. So the first thing I'm doing is that I will go to the Code Aster website training session, and here on the left you have advanced training and you have nonlinear analysis. So in this presentation, if you go down to the page 48, you have the instruction on how to use nonlinear in Code Aster, and basically you have the commands that will make it which are necessary in order to use Code Aster. So I'm not going to dive again in this because I already talked about that in my previous video on the plate with a hole. So I'm just going to show you how I will do that in the software. So the first thing we need is, this is a nonlinear static analysis. So there will be a notion of pseudo time. So it's not real time, but we need to have division of time. And I will need to divide this loading with a function called the ramp function. So this is the first thing I'm going to do. I'm creating in the function table here a ramp function. So let's call it ramp, like that. And this function will be in function of time. So depending if you have activated or not the translation, time is here. Okay, time. So if you have not, so this button basically change business or in the translation. So if you do not activate, the name of the parameter is inst, but if you activate it, it change in time. So it's a bit more convenient to have this translation here in time. Now I need to put some coordinates for that. So I just activate coordinate option, and I will, this will be a very basic function. At 0, the value will be 0, and at time 1, the value will be 1. So if I draw this function, it's a simple line like this. So in French it's called a ramp, so that's why it's called ramp, like that. So okay, so I created that, and this function will be used to multiply the boundary conditions later on when I will create the nonlinear static function. So to create this this simulation, I need also a certain number of increments. So I need to divide this into and create a list of real numbers. So this is into here, defi list real. Okay, so this will start at 0, and I'm gonna give some intervals until 1, and you can specify the step length or the number of steps. So I'm just gonna do it in 100 steps for the moment. Okay, okay, and let's create the nonlinear analysis. So before I actually give some hardening curve and all of that, I want to make sure that it solves as a nonlinear type of simulation. So I'm gonna deactivate this for the moment. So you see this becomes red because some of the parameters were linked to that, so it's okay. I'm gonna go in analysis and use this stat nonlinear. So this is what will be used to do this nonlinear analysis. So I need the model, I need the material, so I have all of that. The increment, so I have it. I just created this list. Okay. And let's see. So I need some kind of behavior. So comportement is the behavior law of the model. So for the moment it's elastic, so I think there should be some elastic law or something, relation elas, so elastic. So I'm gonna go and use this. And I think for the moment it's no, I need the excitation. Yeah, so that's where I define the loads. Yeah, so if you activate the business language, you get loads here. So it's a bit easier to understand. So I have two loads: the boundary condition, which I need to multiply by this ramp function I created, and I'm adding a second one, which will be displacement. So here, and we'll multiply also by the same function. Okay. Now I am gonna add this time a calc champ, so to add some additional type of results in the calculation. So let's see what I want. I want the volumetric stress, so which will be in criteria. Business language is not really ready for everything. Okay, so we're gonna use this sig elga sigma, which means sigma equivalent at gauss points, sig elno and sig no. Okay. And I also want the strain, so I need to activate deformation. And there are several types of definition. There is EPSI and there is EPSJ. So the difference between the two is that EPSI is for elastic linear type of strain, and this one is for large deformation. So for the moment I'm still in the linear, so I will use EPSI, but I am going to change that after when I'm going to switch to nonlinear. Okay. Oh, and I forgot something. The name of this calc champ should be the same as this, so it should be res non L. Okay, should be the same name, otherwise it won't work. Now let's open this output, which is displayed in red. Let's attach the results of this nonlinear simulation, and let's save everything and let's try if that works. So let's create a new analysis case. Let's run that. Let's try this type of elastic solve, but in a nonlinear type of simulation. So you see, I'm going really step by step. At first, I'm doing a pure elastic static simulation, linear static simulation. Then I'm switching to nonlinear static, but without any type of nonlinearity. And then I will add the nonlinear behavior law, the hardening curve, and then by going step by step like that, I assure that this will work. So you see that it takes much more time, and that's normal because it's a nonlinear run. And it's green, so we're okay. We're okay to do that. So I can review the results again just to be sure that we are still doing the right thing. Let's look at the displacement. Let's go to the next step and rescale the data. And now I should be, oh yeah, I have to add a filter for the deformation. So common warp by vector, like that. And also I like to increase a bit the speed of the animation, so I have to go in the animation view and switch to sequence. I think this will be faster. Yeah. So this is what I'm getting now. I'm getting a nonlinear simulation, which it looks pretty much similar to my previous linear static, right? But the only difference is that I have increments right now. Okay, so now we're ready to set up the nonlinear hardening curve to have a real nonlinear simulation. So let's delete that. I think every time I need actually to delete those results and reload them. So the reason I'm doing that is that the HDF file itself doesn't bulk up and become very large, especially if you save different kind of results in it. Okay, so let's go back to Aster study, and let me show you right now how to add the nonlinear hardening curve. So let's add a few changes in the model. So the first thing I'll do is to define the hardening function. So I will need to have some data for this hardening function, right? So I have those data in an Excel file. So let me open that and show you this curve. So this is a full stress strain curve. So I have the elastic portion, which starts at 0, and I have the hardening, plastic hardening part of the curve. So I will only have to input this part of the curve, so I will not input the 0, 0 part. So those are the data that I will gonna have to put into Aster. So let's go back and let's create a function. So defi function, like that. Now we need to define the value of the strain will be defined here in abscisse. So abscisse means x coordinate. So yeah, if you activate here, you will see this name. So edit here, and here we need to input all the values of those. So you can do import table. So I know that works. So what I'm going to do is just you'll see. First, what I'm going to do is put two values. So let's put 0 and 1, and I will edit the text version of this function after, you'll see. So this will be faster than putting all the values here. So x coordinate, then I need to put the y coordinate, and the parameter name will be ipsi. So this is the strain. Y coordinate, the same. I will put for the moment 1 and 1, and you'll see that I'll change that right after. I will need to add some interpolations here. So linear, right and left extension will be linear as well. I'm not sure I will need that here, but nevertheless. And this function will be called hardening. Harden. Let's harden F, like that. Hardening function. Okay. Now those are not the right value, so what I have to do is to I think I can turn this into a text mode, like that, and edit directly, edit the concepts, in this function here. How can I add this one? No, that's not. I just need to edit. Yeah, and the value which are here, abscisse and ordinate, so that's what I need to replace with the actual value in my Excel file. So I have a CSV file which is already in the right unit. So let's open this. Let's open that with a text editor. Open with other application. Maybe with text editor. Yeah. So I'm gonna take those values here and directly paste them here. Oh. Okay. And I'm gonna take those values here and paste them there. Okay, close. And now I am gonna do the graphical mode to come back to previous. And if I now open my hardening function and I have a look at those data, you see all the data have been correctly put inside it. Okay, so I don't know when I click here it doesn't work, so but should be working. So that's much faster than entering those results one by one. Maybe there's another way to do it, but you know, that's the way I found which was the fastest. Okay, so now that I have this function, I have to assign that to the material. So let's go into my diffie material. Yeah. And I can actually change the name. Let's call that steel. And I need to add some traction. So let's find the traction keyword. And let's add my hardening function here. Okay. So I have it here. So I now have my elastoplastic model. Let's go into my nonlinear function here. Let's open the behavior and change this ls to Vemis ISO track. So that's the model with isotropic hardening, and we'll use this Salome for large deformation. Okay. Now we need to set up a few other parameters, because now that we have some real nonlinearity, we need to use the Newton method. I probably have to refine the mesh as well, because this is really not a good mesh. It's just one layer of first all the tetra. This is horrible mesh. But you know, like I told you, it's not, the purpose is not to get correct result for now. So here I'm putting Newton as the method, and I have various ways to control the convergence of this. So for the moment, let's just use the tangent matrix, so that the tangential matrix is recalculated every step. That's the only thing I will do here. Let's activate the convergence option, and let's add some, so maximum iteration, let's put that to 30 instead of 10. Okay, I think that's all I need to really solve this. Now there's one more thing I want to do, or two more things, yes. One thing is I want to have, if an increment is not converging, I want to have an automatic cutting of the increment in 2 steps. And so in order to do this, I have to create a diffie list int. This will be based on my list of increments that I have defined first, and I will use the method automatic. Échec means failure, so, and this will be when I have a failure, it will automatically divide my increment, and I want to do that up to 3 levels, so I have to activate this. Okay, I think it's good. Def list nos execute one keyboard list int. Okay, I don't know why it didn't take into account this. So this will be times, and what I have to do is to go back into my nonlinear and change the list of increments. So instead of giving this, I'm giving that. That will help to do the automatic division of my increments. That will be very useful. And the second thing I want to do is to limit the number of results plotted to the file, because I'm getting very large files. I have 100 increments, so each increment will give me a lot of results, and at the end, you know, I will get gigabytes of data. So what I need to activate is this function archivage, which in business language is storing. So I need to create another function. So defi function, sorry, not, I need to create another defi list real list, which will start at 0. Let's call that storing. And this time I want it to go until 1, so like my increments, and I want to have number of steps of 30, so maybe even less, let's put 20. So which means that it will only print the results to the file every 20 increments, but it will calculate 100 increments or more. So that will be very useful. So I go back to my stat nonlinear, and I activate this one. Storing. Okay, so now I just have to run that again without breaking down again. And okay, it doesn't work, so I probably have something wrong somewhere. Okay, so in my defi function of traction, I need to have non para obligatoire non valorisé. Okay, so seems like I forgot something. Okay, I forgot something in my okay, I see now. I have a function that has been created here, which when I yeah, that's a mistake. I don't want that. So probably because this function has nothing in it. That's what causes the problem. Okay, let's run that again. Okay, now it's running, so let's wait a bit and let's follow the graph. I like we have this interactive graph that works right now. So you see each iteration of Newton is written here in the message file, so we know exactly which step converged. So convergence has been reached. Well, it's written in French, right? But you know, it's almost over, so I hope it worked. Seems like it converged. Okay, well, it worked. So let's go into my Parvis. looks like I forgot to delete all that. So before I load something new, let's just delete them. So go on the desktop and let's reload my file here. Yep, let's add my warp by a vector. Let's have a look at the displacements first. Yeah, so it seems that it worked. And by the way, you see that this time I have only 20 time steps. So the number of total is 20. I calculate 100, but I have only 20 that have been printed out. So this result file is much lighter than the previous one. If I look at the font means stress, so this stress will be horrible, right? It's probably very wrong. The value here, I don't even dare to look at that because the mesh is not good, but at least it converged. So I got what I wanted. I got the model that converged, and I got my nonlinear material. And we've now reached the end of the first part of this simulation. I told you this kind of simulation is very tricky. So in a second part, we'll really review the most complex stuff, which is really how do you build a very, very good model for nonlinear contact analysis? How do you set up the contact? And we'll go in all the details about this. So about the convergence of the contact and the different kind of parameters you need to set up, and also where you can find all the help that you will need for this kind of complex simulation. So this second part is really, really interesting. Took me a lot of time to make. So and this, if it's not yet on my YouTube channel, it will come in a few days. So the time I edit the video and all this. So thank you very much for watching. And if you learned a lot of things from this video, if you find it insightful, please leave a comment. Please let me know. Please like the video. This is always great to see that some people are learning from what I'm doing. And you know, it motivates me also to create more content. Thank you very much, and see you in the next part.